In this video, we're going to do one sample confidence intervals for mu, the true population mean. If you've already watched the video for the confidence intervals for proportion, this is going to follow the same format for the most part. So for example, we're going to start off by recalling that the basic setup for any confidence interval in this class is point estimate plus or minus critical value times the standard error for that estimate. And that's the standard error of that point estimate. So whether that point estimate is p hat or that point estimate is x bar, we're going to use the appropriate standard error for that point estimate. So that's important. So that's going to be reduced to PE plus or minus CV times SE. So in a given scenario, we just need to determine the appropriate PE, CV, and SE to use, and then we're going to proceed from there. So the example we're going to use in this case is huskies and husky weight. So this is coming from the class notes again. And that's appropriate because to estimate a population mean, we need quantitative variables. So let's go to the first example. This first example is going to set the baseline for comparison for all subsequent examples. So this is going to be the framework for the standard error, the standard deviation, the sample size, and the confidence level. And we'll keep coming back to the results from this example when we do the subsequent problems. So for example, we have a sample of 10 female huskies with an average weight of 41.5 pounds and a standard deviation of 0.6 pounds. Assuming the weight of female huskies follows a normal distribution with an unknown standard deviation, construct a 90% confidence interval for the true average weight of female huskies. The parameter of interest in this case, we're told to find a confidence interval for the true average weight, so that would be a true average or a true mean. So that would be mu, a population mean. So the point estimate, or our best guess for that population mean, would be x bar, and that's our sample mean. And we're given our sample mean to be 41.5 pounds right here. We're told that the average weight of this sample is 41.5 pounds for those huskies. We're going to come back to the critical value in just a minute, and we're going to jump down now to the standard error. Remember, I said on that first page that the standard error is the standard error of the sample statistic, which in this case is x bar. Because we have an unknown standard deviation situation, we're going to use s over square root of n to calculate the standard error. S is the sample standard deviation, which we're told is 0.6 pounds. So we're going to do 0.6 divided by the square root of our sample size, which is 10, because we're told we have 10 female huskies. So when we do this, our standard error works out to be 0.1897. Now finally we can come back to this critical value that I left hanging. The critical value is going to be a t with new degrees of freedom and 1 minus alpha over 2 left tail probability. And that's just in keeping with always having left tail probabilities in the subscript of our critical value. So we need to identify nu, our degrees of freedom, and we need to identify alpha. So alpha is going to be easy. Alpha is 1 minus our confidence level, which in this case is 0.9. So alpha is going to be 0.1. Alpha over 2, therefore, is going to be 0.05, giving us 1 minus alpha over 2 of 0.95. Nu is the degrees of freedom, and that's going to be n minus 1. We subtract 1 because that's the number of parameters we are estimating. Here we're only interested in one population mean. This is a one sample case. So we're only estimating one parameter. That only costs us 1 degree of freedom. So that's going to be 9. N minus 1, 10 minus 1 is 9. So we're looking for a t with 9 degrees of freedom and 95% or 0.95 probability to the left of it. We get that from the t table. So here's our t table. Now we want t with 9 degrees of freedom and 0.95 left tail probability. But we see here that we're given right tail probability. So all these probabilities listed up here in the column headers, these are all right tail. So if we have 0.95 in the left tail, that means we want 0.05 in the right tail. So both via this graphic and by telling us this is the upper tail probability, they're really emphasizing that they're doing things a little different from our notation. So that takes care of one part of it. We still need our degrees of freedom, our nu. And so that comes over here in this far left-hand column. So we want 9 degrees of freedom, so we're going to come down here until we have 9 degrees of freedom. So we have 9 degrees of freedom. We want 0.05 probability, and that's this t-score right here. And that's going to be 1.833. So back here on our worksheet, we have our critical value of 1.833. So these are the three values that we need. We have our PE, our CV, and our SE. So we can write our 90% confidence interval for mu to be x bar plus or minus t with 9 degrees of freedom and 1 minus alpha over 2 probability to the left times s over the square root of n. So this is our most general form, so always write your formula or the equation you're using. And then we do our substitution. So our substitution, well, we're just plugging in the numbers that we just found. So that's going to be 41.5 pounds plus or minus our t of 1.833 times our standard error of 0.1897. Now we have to add like units, so it turns out that this standard error is in the same units. Our standard deviation is in pounds, so our standard error is in pounds. So we're okay, we're adding pounds to pounds. And we finally solve this. It turns out our confidence interval for mu at the 90% level is 41.153 up to 41.847. And the units on this, again, is in pounds. So we're 90% confident that the true weight, or the true average weight, of female huskies is contained by this interval. So let's see our second example. We have a sample of 10 female huskies with an average weight of 41.5 pounds and a standard deviation of 0.6 pounds. Assuming the weights of female huskies are normal, with an unknown standard deviation, construct an 80% confidence interval. So the only thing that's changed here is our confidence level. So our PE, well, that's just still our x bar, our point estimate. So x bar equals 41.5 pounds. That's easy. That's unchanged from example 1. And our SE, well, that's unchanged. That's still going to be the standard error of x bar. And because our standard deviation and our sample size are unchanged, that s over the square root of n, that's still going to be 0.1897 pounds. That's unchanged. So by changing the confidence level, the only thing that changes is our critical value, which is nice. We don't have to do too much extra work. So our critical value, remember, is t with nu degrees of freedom and 1 minus alpha over 2 left tail probability. So we're going to have t, well, that's still going to be 9 degrees of freedom because our sample size is unchanged. And we want alpha here is now going to be 0.2. So alpha over 2 equals 0.1. So we need t with 9 and 0.9 probability. So here on our t table, we're looking for the t with 9 degrees of freedom and 0.9 left tail probability. And remembering that this only gives us right tail probabilities or upper tail probabilities, that means we want a 0.1 right tail probability because that's what's left over when you do 1 minus 0.9. So we want 9 degrees of freedom, that 0.1 probability, and that's going to give us a t of 1.383. We come back to our workbook, we put 1.383 for our critical value, and we have everything that we need. So we can write an 80% confidence interval for mu that true average weight of female huskies is x bar plus or minus t with 9 degrees of freedom, 1 minus alpha over 2 probability, times s over the square root of n. And now we plug in. So we have our formula and we have our substitution. So 41.5 plus or minus 1.383 times our standard error 0.1897. When we solve for this confidence interval, we get our answer to be 41.2376 up to 41.7624, and the unit on this interval is pounds. So we see here that this is a narrower interval than in 1. Over here, this is our confidence interval. This is at 90%, so alpha equals 0.1. Here, alpha equals 0.2. By increasing alpha or by decreasing our confidence level, we decrease the width, all other things equal. So this next example, we're back to a 90% confidence interval, but now we have n equals 50 for our sample size. We still have a sample mean of 41.5 pounds and a sample standard deviation of 0.6 pounds. We're still going to assume that the weights of female huskies are normal with an unknown standard deviation. So let's construct this 90% confidence interval with a larger sample size. Our point estimate is still going to be x bar, and our x bar is our sample mean. It's that 41.5 pounds. So this is still unchanged from question 1. Our standard error is going to be SE of x bar, the standard error of our sample mean, and that is s over the square root of n. Well, s is unchanged. S is still that 0.6, but n has changed. N is now 50. So 0.6 over the square root of 50, it's actually a dramatic decrease because we're dividing by a much bigger number. So our standard error is now 0.0849 pounds. So I'm going to say this is much smaller than in 1. Just so we have a note to ourselves so we can see what's staying the same and what is changing. Now our critical value, even though our confidence level is staying the same, because we have to take into account the degrees of freedom, which is in part based on the sample size, we will have a different critical value. So our critical value, remember, is t with new degrees of freedom and 1 minus alpha over 2 probability. So this part is the same, but this will change. So let's figure that out. New, remember, is n minus 1. 1 is the number of parameters we're estimating. We're just estimating one population mean. So this is going to be 50 minus 1, or 49. That 1 minus alpha over 2, alpha is going to be 1 minus 0.9, or 0.1. So alpha over 2 is going to be 0.05. So we need to go to the table and find t with 49 degrees of freedom and 0.95 probability to the left of it. So here we are back at our t table, and remember we're looking for a t with 49 degrees of freedom and 0.95 left tail probability. And again, this table only gives us right tail probabilities and it only gives us upper tail probabilities. It really emphasizes that graphically and in the header of the table. So 0.95 left tail probability, that's the same as 0.05 right tail probability. So we just need to find that 49 degrees of freedom in that leftmost column. So we come down here and we look for 49, and we get here and we see it goes from 40 up to 50. And we say, what? Is this a problem? And it turns out it's actually not. What we do is we say when we run out of resolution in the table, when the table doesn't present all the degrees of freedom that we need, such as in this case, we round down. So don't panic, just use 40, because you never want to claim that you had a larger sample than you really did. So think about that. If we used 50 instead, to get 50 for the degrees of freedom, we would have had to say n minus 1 equals 50, which means that n would have been 51. But we didn't have 51. We only had 50. That's how we got to 49 in the first place. So we're going to round down and use 40 as a conservative estimate. So we're going to use 40, and we're going to go over here until we get to that 0.05 right tail probability, which gives us 0.95 left tail. So our t critical value is going to be 1.684. And we'll bring that back over here. So we're going to say, instead, use t with 40 degrees of freedom and 0.95, and we're going to use 1.684. So we're going to say this is approximately equal to t with 40 degrees of freedom, 0.95, 1.684 for our critical value. We're being very thorough here. So now we have our point estimate, which is unchanged, our critical value, which is changed. This is smaller. And we have our standard error, which is also changed for problem 1, which we've noted, which is a lot smaller than problem 1. Those changes are again due to that larger sample size. N has gone from 10 to 5 times as big, up to 50. So our 90% confidence interval for mu, we're going to be very thorough, x bar plus or minus t with new degrees of freedom, 1 minus alpha over 2 probability, times s over the square root of n. We're going to plug in 41.5 pounds plus or minus 1.684, which is our conservative estimate for t, because we rounded down our degrees of freedom, times our standard error, 0.0849. And our confidence interval therefore becomes 41.3577 up to 41.6423 pounds. And we can see, relative to the example in problem 1, this is very relatively narrow. So, all things equal, increasing the sample size n narrows the confidence interval. It gives you a smaller range of values. And that's because the t value decreases via nu and SE decreases. In this example, we're back to our original sample size of 10 huskies, but we've changed our sample mean. Instead of being 41.5 pounds, it's about 3 pounds lower at 39 pounds. But the standard deviation is the same at 0.6, and the confidence level is the same at 90%. So we have n equals 10, x bar equals 39, s equals 0.6, and confidence level of 90%. So let's pull out that information and get the PE, CV, and SC we need for a 90% confidence interval. So we're still estimating that true mean, so PE is going to be x bar, and again here it's 39 pounds, and this is lower than in question 1 than our original example. The CV, well, fortunately we don't have to go back to the table because this is going to be t with nu and 1 minus alpha over 2 degrees of freedom, but that's nu is 9, and 1 minus alpha over 2 is 0.95 because we're back to 90% and 10 observations. So this is that 1.833. So this is the same as in 1. And finally, the standard error. This is the standard error of our sample mean x bar. So even though our sample mean has changed, that doesn't matter because the standard error is only based on the standard deviation and the sample size. So this is s over the square root of n, which is equal to 0.6 divided by the square root of 10, which is that old standby 0.1897. And this is also in pounds. So this is unchanged from 1. So the question here is, if we have the same critical value as in question 1, and we have the same standard errors in question 1, and all that's changed is the point estimate up here, how does the confidence interval change? So the 90% confidence interval for mu, well, that's x bar plus or minus t nu 1 minus alpha over 2 probability times s over the square root of n. This is just developing good habits, folks. It's 39 pounds plus or minus that 1.833 times 0.1897. And that gives us a confidence interval of 38.6522 up to 39.3478. And that's in pounds. So if we look at this, this is the same width as problem 1. And we've been comparing widths the whole time. So what's changed? It has just been recentered on the new sample mean. We've shifted the whole interval down. So this interval from problem 1 and this interval from problem 2, they're the same width and they cover the same quantity of values. It's just the actual values change because we've shifted it. So now for our last example, we consider the situation where we have 10 female huskies. The average weight is back to 41.5 pounds for the sample, but that sample standard deviation has ballooned up to 2 pounds. There's a ton of variation in the sample, and we want a 90% confidence interval for the true average weight. So our point estimate, as it's been this whole time, is x bar, and that's back to 41.5 pounds. So that is unchanged from problem 1. Our t critical value, well, that's unchanged from problem 1 because our degrees of freedom are unchanged. That's still based on n equals 10. And because we're dealing with a 90% confidence interval, that won't change. So our t with nu and 1 minus alpha over 2, that's going to be t of 9, 0.95, and that's going to be 1.833. So that's from problem 1. So our standard error, this is where that standard deviation that has changed comes back in. So standard error, that's the standard error of x bar, the sample statistic we're using, and that's s over the square root of n, or 2 over the square root of 10. Before we were dividing 0.6 by the square root of 10, but now we're dealing with a number quite a bit larger, so our standard error is going to be 0.6325 pounds, and this is much bigger. So we have the same point estimate, the same critical value, but a much bigger standard error. How does that impact our confidence interval? Well, we build a 90% confidence interval for mu using the same formula that we always do, x bar plus or minus t nu 1 minus alpha over 2 probability times s over the square root of n, and we plug in our values. 41.5 plus or minus 1.833 times 0.6325. And when we solve for this, our confidence interval is 40.3406 up to 42.6594. Comparing these two, this interval is much wider than the interval from 1. So increasing the standard deviation, all other things equal, widens the interval. It makes the interval less precise. So that's what happens mathematically when you change different aspects of the confidence interval, when you change the sample standard deviation, when you change the sample mean, the confidence level, or the sample size. Let's see what happens pictorially. So this is a really handy web app, similar to the one that we saw before in the previous video when we were doing confidence intervals for the proportion. In this web app, if you have the raw data, you can enter those individual values. So for example, if we knew those 10 weights for those 10 huskies, we could enter those data here. However, we have the summary statistics, so we're going to choose that option and enter those values ourselves. So for the first example, we have a sample size of 10, a sample mean of 41.5 pounds, and a sample standard deviation of 0.6 pounds. Furthermore, even though the default confidence level is 95%, our problem was interested in a confidence level of 90%, so we're going to change that. Over here on the right-hand side, we see what's output. Now, if we had entered our raw data, seeing this table would be really nice because it would summarize the mean and standard deviation for us. However, since we input them directly, this table is just telling us what we already knew. Now we got a summarization of some information about our sample beyond what we'd already input. So we get our point estimate back, which is the value of x bar, our sample mean. We get the standard error, and this is that same standard error that we calculated. This is that s over the square root of n. And then we get the margin of error, which is the standard error times the appropriate t critical value. And that t critical value takes into account the confidence level that we input as well as the sample size. So we come down here and we look at the confidence interval that the web app calculates, and it gives us 41.152 up to 41.848. And we had 41.153 up to 41.847, so that's pretty close. I would argue that that's just within rounding error. So this last item is similar to what we saw in that previous video as well. This is a visual representation of what our confidence interval does. So down here we have a number line, and this number line for now is just going from 40 to 42 to 44. So this is a pretty coarse number line. And our point estimate x bar was 41.5. So right down here, if we were to drop that down to that number line, this is where 41.5 would be. And these whiskers extend down to the lower bound. So this whisker goes down to 41.1522. And this whisker goes up to our upper bound of 41.848. And so this confidence interval, or the width of this line, tells us the width of our confidence interval. If it were a longer line, we'd have a wider interval and it would capture a wider range of plausible values. But because this line is fairly narrow, only values that fall within this range are reasonable based on our sample data and our sample size, or at least those are the ones that would be believable for that true population mean. So let's see what happens to this line when we change our situation. In the next example, we went from a 90% confidence interval, kept everything else the same, and just went to 80%. We can see that our interval narrowed just the slightest bit, and it's easier if you look at the numbers. They went from 41.153 to 41.847 to 41.237 to 41.76. So this is just the slightest decrease. Our margin of error is just the slightest bit smaller, but that's because we already had a fairly large standard error because of our sample size. So just losing 10% confidence didn't cost us too much. We're still covering roughly the same range, but it is slightly smaller. These whiskers did contract just the littlest bit. So let's make this 90% again. And you can see, oops, they jumped out just that much because we are covering a wider range. More confidence means more numbers. And see what happens when we hold everything else equal, but increase our sample size to 50, like in that third example. And you can see here, this is quite easy to see how much smaller this interval is. And that's because this margin of error is tiny. Our standard error here is so small. So all other things equal, as we saw when we did the math, but here we get that nice visual representation. X bar hasn't moved. All that's changed is that we're covering just this tiny, tiny range of values. So let's go back to a sample of size 10 and see just how that jumps. And what if instead of a sample mean of 41.5, what if our sample mean was 39, like in our fourth example? Well, here, all we did was basically pick up our interval, which had been up here at 41.5, and shift it down almost 3 points. The width of this interval is the same. If we look at the margin of error, it's the same. The standard error is the same. All that's changed in all of these values is because of the change in the point estimate. So we've just taken this interval, that same width interval, and moved it down to 39 from 41.5. Finally, let's move our interval back up to 41.5 where it belongs, that sample mean that we had. We had a sample of size 10, but say, remember that last example, we had a standard deviation of 2. Look how wide that interval is. Look how big this margin of error and standard deviation are, or that standard error are. That gives us giant whiskers. So this X bar is still being projected down to 41.5, but I'm stretching out way lower, way higher on this number line. I'm encompassing a much wider range of plausible values. So all other things equal, changing the confidence level, or changing the sample standard deviation, or changing the sample size, or changing just the sample mean, will have an impact on my confidence interval in a predictable way. And we have seen that visually using this web app, and we've seen it mathematically comparing what happens when we work through the examples ourselves.